All right. So yeah, as Jesse mentioned, so I'm going to be talking actually about some new results that we have just put out recently on our Earth systems model for reliable and skillful predictions called AERIS. Actually, before I do that, sure. So this is, I'm the one here presenting it, but this has really been a culmination of this is really the culmination of a many-year, multi-institutional, many late night, big team collaboration. And so even though I'm the one up here sitting here and talking about it right now, it's a whole other people, a whole group of us that really all made core contributions to this project. Varuni is one of the authors. WeHo, sure, a couple of other people that are probably here that I'm missing. But so this is really a team effort, and so I, yeah, am up here talking, but I'm not trying to take all of the credit. Also, I am not a climate scientist by training, so my background is in high energy physics, and so the domain, if there are any domain experts in the audience, take it easy on me. If there are any actual pressing questions or anything that is too technical, I think Jason's actually one of the first authors and is on the Zoom. So if there's anything that anybody really wants to ask more questions about, he is also available. So right. So this model, this AERIS model that we have just put out. So the publication came out a few weeks ago, and it is a finalist for the Climate Gordon Bell Award at supercomputing this year. So that we found that out just recently, and so that was a huge win for the team and a great thing to hear, obviously. So yeah. So what is this model? So it is a SWIN-based diffusion transformer model for predicting short to subseasonal to seasonal forecasting. So it's a weather generation model. It was trained on 1/4 degree and 1.4 degree ERA 5 data. So this large, historical ERA 5 data that is laid out on this grid, kind of as shown here on the left. The model architecture, so it's using a variation on a SWIN transformer with a diffusion backbone for the probabilistic generation. And this figure here on the left is a 2-week rollout of the specific humidity at 700 meters. And, just qualitatively looking at it, you can see that it managed to capture the dynamics through this 2-week rollout, which is, somewhat impressive if you've worked with these models or are familiar with these sorts of models at all. Being able to capture these long-term dynamics is something that is highly desired for these types of models. And so this is obviously something that is good to see. Relative to the computational cost that would be necessary for doing this high fidelity of a simulation using traditional techniques, so like the global forecasting system, which relies on numerical methods, it's about an order, between 10 and 100,000 times faster. In terms of compute resources required to generate these high fidelity forecasts. And so the potential for AI accelerated weather forecasting to really kind of lead to huge breakthroughs in long-term, and being able to predict extreme weather events more early and more accurately. Even things like super long forecasting is, there's a lot of recent research in this area that seems to suggest that generative-based modeling is advantageous for these weather-based simulations. And this model certainly seems to support that point. So the core contribution, so AERIS, so this is the first billion parameter diffusion model for weather and climate that operates at the 1x1 patch size. So it operates on a per pixel level and generates 1x1 patches, which correspond to individual pixels. It is guided by physical priors, so it has there is some notion of there is physical intuition baked into the priors that make up the different physical variables that are used for training. And so there's a lot of, this is one of the things that I think actually is probably has the most room for improvement, especially as far as like physical based models. I think there's a lot of room still for improvement for better incorporating physical priors and to really incorporating the true geometry of the sphere that could be, looked at further. But at any rate, this is when we look at comparing this model to similarly sized models, such as GenCast from Google. We see that it's competitive with GenCast and outperforms the standard IFS ENS simulations, which is at a baseline an improvement, right? Like if you're improving upon IFS, then you're already doing better than traditional forecasting methods. So being competitive with GenCast on a similarly sized model is actually a pretty big accomplishment. We were able to do this in large part due to our creation of this swipe parallelism technique. So it is a kind of new parallelism technique that we invented specifically for training this large scale, high resolution climate model. So it's a 3D hybrid parallelism strategy that incorporates traditional sequence and pipeline parallelisms, as you would see in traditional LLM training, but also incorporates this idea of window parallelism, which acts on the windowed attention blocks from the transformer model. And this, by increasing the degrees of this swipe parallelism, we are able to scale up to very large GPU counts while maintaining a reasonable batch size. And so for this work in particular, we were able to achieve a sustained performance of over 10 exaflops on 99% of Aurora. So I think a little over 121,000 XPU devices total, which is, off the top of my head, I don't remember exactly, 10,000 something nodes, which is about just right there at the upper limit for all of the nodes that we have of Aurora. And so that was a tremendous effort, honestly, to get those of you who have been on the system and worked with Aurora, especially at large scales, or probably might be familiar with some of the challenges that you face at increasingly large scales. And so to get PyTorch and one API level and all of these things to kind of work together and be able to orchestrate this computation across the entire system was really took a lot of effort and was a very big accomplishment, I would say. And as far as I am aware, the best scaling result that we have seen come out of Aurora. So that's just all around really just great results. So the model this is kind of more specifics on what the model was used for training and some of the physical variables explicitly that we were used for training. So in particular, we are one of the probably most physical variables that most people have a kind of physical understanding of is the 2 meter temperature, which measures the obviously temperature at 2 meters above sea level. The U and V components of the wind, the specific humidity, and geopotential are really, I would say, the core physical variables that drive, that are being simulated and modeled that we're interested in looking at and evolving in time. There are also these abbreviations, so like things like if you see MSL, it stands for the mean sea level pressure. Me not being a climate scientist by training, and having to remember more acronyms is challenging. So this is even maybe a little partially for my own remembering. But at any rate, so these are the variables of interest, and you can kind of have one thing that I think is kind of nice about doing this climate modeling in general is that everybody has some understanding of the weather, right? Like there are a lot of science domains that are beyond, just completely out of your realm of expertise, or something that you just have no sort of physical understanding of, and so it makes it that much harder to understand or grasp. But one of the things that's been nice about working on this project is that Yeah, I don't know. When you talk about the wind speed, right? Everybody knows what that means. And so you kind of, I don't know, it's a bit more physical than some of the other projects I've worked on. And it's, yeah, been interesting to see. Yeah, I don't know how all of this really comes together for a model that is able to actually predict the weather more accurately than current forecasting techniques. So it's yeah, very impressive to me. Like I said, this is not something that I have done historically, and so all of this is, yeah, just incredible to me, in my opinion. One of the things that actually makes training these models challenging in general is that the resolution of the data that so in order to train the best model, you want to use the highest resolution data, right? The highest resolution data I can use is going to give me the most information, will allow me to most accurately predict, all of these different variables of interest. And so the finest resolution that we have currently of the data is this quarter degree. So I think that's a little over 30 kilometer grids that partition the Earth. And so that quarter degree data from 1979 to 2020 is about 30 terabytes worth of data. And so it makes working with it, very challenging in general, especially when you need to move it between systems, and yeah, try to deal with it in a reasonable fashion. It's just very large and it can be very challenging. And one of the things that we actually spent a lot of time on, I don't know if Huiho is here somewhere, maybe not, but as you try to increase your model capacity, one of the very big challenges is that you're already using so much of your available memory just holding the data. Just in order to do a forward pass of my model, I need to load in the data and hold all of my model weights, optimizer states, and everything else in GPU memory. And so as it becomes very difficult to try to scale up to large models when I'm taking up 20 gigabytes of GPU VRAM with just trying to take in a single batch. And so there's a lot of actually really interesting work that has been done on like the data ingestion pipelines and ways to cleverly split variables up so that you can work on them in separate parts and these types of things. And so there's a lot more that I could talk about related to the data actually that I think is super interesting. And if you manage to find Huiho later this afternoon, he would be also happy to talk more about this, I think, because he has done a lot of the work on the data optimization and ingestion pipelines generally. So yes. So where did we start for the kind of inspiration for this whole project, right? So when we started working on this, there were all of the state-of-the-art climate models were using some variation on a vision transformer backbone, essentially. And they were all deterministic, using large, vision transformer-based models that worked, kind of as you would expect for a typical vision transformer model. They use what's called this windowed self-attention, which is beneficial for weather modeling in particular because it allows by splitting the image up into windows, it allows you to capture both local and long range details from the image and pass that through to the network, which is an inherent limitation of a typical transformer. So one of the things that's nice about breaking this up into windows and working on having your attention be localized to small patches spread across multiple windows allows you to work on all of those windows separately and then kind of aggregate the result. And so this is actually what inspired the window parallelism technique that we've adopted. So we kind of built on this idea of this windowed self-attention, and in combination with a few other kind of clever parallelism techniques, we're able to split up this self-attention mechanism effectively across all of the GPUs in our job. And so by doing that, we're able to effectively kind of split up all of the work, all of these windows across our GPUs effectively and in a way that scales up to very large node counts without too much of a performance hit, actually. So that's another major point of this, that we were able to get this additional parallelism degree by splitting up the windows without incurring as much of a performance hit as you might expect trying to do a 2D parallelism technique. So we also took some inspiration from some of the state-of-the-art large language models, so things that have came out in the literature more recently, like two-dimensional rope, the two-dimensional rope embeddings, RMS norm, Swiglu. And so we took kind of all of these ideas and built them into this architecture, which as far as I'm aware, is that we were the first people to kind of take these modern LLM approaches that have shown to be useful in recent LLM results and apply them to the vision transformer backbone of this SWIN transformer. And so we did some pretty early ablation studies on this and found that it was advantageous in the experiments that we were able to do. We weren't given the cost of training this model at scale. We weren't able to actually do explicit comparisons for all of these changes that we suggested, but as the model shows, I think that they ended up worked at least as well as what we would have used otherwise. So I think by adding the two-dimensional rope allows you to really kind of increase the dimensionality of your embedding space, which I think is probably useful for the diffusion generation. But there's a lot more details about that I'm kind of just glossing over for the sake of time. But it's mostly a variation on the standard SWIN transformer architecture with these specific additions of things like the 2D rope and the Swiglu instead of Gelu and things like that.
Sam, one question. So
Absolutely.
So you're using different models for your model, is that correct? Like your SWI, GL, and then RMS norm? I'm trying to understand the detail.
Sure. So I know that people love to see these model architecture diagrams, but and I don't know, in my opinion, they're not always terribly insightful, especially like at first glance. But so sure, I can kind of walk through it. So like, what this is really trying to show is this. Oh, you know what? Here, can you? Whoa. Oh, that's fine. You can still see it, right? I think I can draw on here. Sick. So really what you're interested in is like this block that shows up, right? Yes. This here is really the actual architecture that data gets passed through. So you take in the time for an input. So the initial condition, the initial data, the generated configuration, and the target, along with the time embedding, gets first passed in through this positional encoding, through this patch embedding, into a stack of n attention blocks that are illustrated then. So this pop out here on the right is just this like a zoomed in view of the attention block. And so this is just the details of the attention mechanism specifically. And so it's just your standard attention data architecture in general, with the addition of the two-dimensional rope. And I suppose that's really about it. We have the traditional gated attention that we'd see in the SWIN transformer. And so we take as input a initial condition, the generated configuration and the target, pass it through our network, get as output this difference between the initial and output configurations, which tells us the amount by which our initial state has evolved, essentially. And so this is maybe a bit more clear on a later slide. You can see it's a bit more clear exactly how the data propagates to the network, actually. But so when we had started working on this, all of the existing approaches were using just standard vision transformers, which have the unfortunate side effect of being are inherently deterministic, right? For a single input, you get a single output. which when you're generating tokens is perfectly acceptable. But when I'm trying to generate weather forecasts, I would like to have a bit more flexibility if possible. And so obviously one of the limitations with the standard vision transformer is that for a single, snapshot input, it will generate only a single snapshot output, which, obviously is not exactly what, not as good as it could be. And so we can do a bit better than that by introducing a probabilistic or a generative component to the configuration generation and by doing this, it essentially allows us to take an initial, for a given initial condition, it allows us to generate an ensemble of output predictions according to some distribution. But that's really useful for giving us a better understanding of, being able to try to predict uncertainty and variability in our predictions. It gives us some notion of error and confidence in our predictions, and also allows for risk assessment and better forecasting in general. And so this slide here actually kind of maybe shows probably a bit more what you were looking for, Yasi, actually. So if people have, if I've completely lost you and you have no idea what I'm talking about, hopefully this will make a bit more sense. So this is kind of how the diffusion transformer model approach works. So you take as input some, snapshot. This is some individual grid cell of some, physical variables measured on at some height above sea level. And so I take this as input, as well. So this is, given as input, I have this input data. In addition, I do this so during trading, I do this reverse diffusion step that consists of multiple individual sampling steps. Each of these individual sampling steps is essentially trained to remove the noise from the previous step. And by doing this successively, starting from a completely noisy image, I'm able to approximate the input by doing this, by training the model to be able to do this. I am eventually able to more accurately reconstruct that input image. And once I have reconstructed my estimate of the input image, I can use that input, my estimate, and the target through some objective function that can then be evaluated, which gives me a gradient that I can then backpropagate through my network, and so on and so on. And so by doing this kind of inner diffusion step, I'm able to turn what would otherwise be a deterministic approach into something that is probabilistic and is able to generate, like I said, ensembles of forecasts, which is, just much, obviously advantageous. So these figures here on the bottom are not the best, unfortunately. I put this the first iteration of the slide deck. But this figure here on the left is an illustration of the reverse diffusion process. So in this process, it's starting from the noise distribution and evolving into the target distribution. So the numbers aren't terribly easy to see. Maybe I can blow this up. Yeah, sick. So once it gets, whoa, I wasn't trying to do that. Once it gets back to zero, you can see that at zero, the dots are much more uniformly spread. You can see that that's coming from I don't know if it's exactly uniform, but at the starting point, you can see that the dots are clearly much more spread out in general. And then this example, I think in particular, is actually using Langevin sampling. So it's just a single diffusion step between successive updates. But you can see that by running this reverse diffusion process, where I slowly subtract the noise at each successive sampling step, I'm able to start from complete noise and gradually, at each sampling step, remove a little bit of that noise until I get back to the actual target distribution. And so this is the process that we are trying to learn to do. And yeah, really in my opinion, the easiest way to think about diffusion models in general is going back and forth between a target distribution that accurately describes your data of interest and complete noise, right? And it's really just a matter of interpolating between those two distributions, depending on how you want to train it. But yeah, I don't really have enough time to go into too much depth on diffusion modeling and right now, but if hopefully this gives like at least a somewhat picture of what is happening behind the scenes. And if, yeah, you're unfamiliar, honestly, I would really encourage people to look into it. I think so this is somewhat what I did my PhD in physics. So I'm a bit biased and think that it is interesting. But at any rate, yeah, I think a different approach than what is currently the mainstream, even for large language model, large language model research in general. I think that diffusion is increasingly there's increasing amounts of research that show diffusion models doing what I would say are pretty novel behaviors and that. And so yeah, I expect that they will continue to be useful and even more impressive in the future, honestly. I did not get to finish that slide. So then what time is it actually? 12:40. So okay, I'm already running pretty low. See, yeah, I told you, yeah, see, I can definitely take the whole hour if you let me. So again, this slide, this slide goes into a bit more detail on the actual implementation of this swipe parallelism technique. It's a bit hard to convey in these two-dimensional images. And yeah, I mean, I think it is clear to me because I helped work on this, but I think seeing these things for the first time, it's not incredibly obvious what is going on. And yeah, I would be able to show it a lot better if I like had a globe maybe, but basically what it is a combination of traditional pipeline parallelism where you have a model that is split, layer-wise vertically across multiple GPUs, in combination with what is traditional sequence parallelism, where you have some long, list of input sequences that you can split up across all of your GPUs and work on in parallel and then aggregate at the end, which are, not new and are just have existed for a while and isn't anything novel. But what we did that was actually interesting is combined those with this window parallelism approach, which is what we're trying to illustrate in this figure here. So here you can see on this, like in the left here, it would be your attention window. And you can see each GPU is numbered by, or each rank that exists on the GPU is labeled by its integer index. And so each component of that attention window sits on an individual rank and are one small component of this patch here in this red square. And by basically, kind of doing this like ring all reduce on ring, not like all reduce, this like ring send and receive pattern on these images across neighboring GPUs, you're able to split up all of these images across all of these different ranks. Each rank essentially processes its local portion of the image and does this kind of neighbor pass and receive. So you can see here in this like bottom, maybe you can't. Whoa, that should be okay. I don't know why that's not bigger. Anyway, so no, that works. You can kind of see here, right? So like GPU N this last GPU will pass to the one right before it. One right before it will pass to the one right before it, and so on until it gets to that first GPU, which would then send it back to the end of the ring. And so by working on the windows in this fashion, in combination with the other two parallelism techniques, it really allows us to very effectively split up the model over large number of GPUs, which allows us to really keep our batch size low when scaling up to very large numbers of GPUs. So this is just details about Aurora that hopefully everybody here at least is familiar with now. and I don't really need to go into too much detail about, but yeah, so I guess the official number that we have available is 127,000 XPUs. And so I said we got to what, 120,000, I think, or so. So very, very significant fraction of the entire machine. And here's here are the actual scaling results. So the most interesting point is this blue point right here. That is, I think, a little over 10. It's like 10.2 something exaflops that we were able to get of sustained performance on 120,000 GPUs of Aurora. And that's, you can also see obviously that it's pretty close to linear scaling all the way up from 720 nodes all the way through 10,000 nodes of Aurora. In particular, we saw the best performance for this 40 billion parameter model, and slightly worse performance for the larger 80 billion parameter model. But you can, as you can see, all of these different model sizes all exhibited pretty damn near linear scaling, which was incredible to see, honestly, and really a huge. It's hard to understate the amount of work and effort that goes into generating a plot like this. And so yeah, it was I'm up here, like I said, I'm one up here standing here and talking about it, but it's really, oh, I did not mean to click stop share. It was really a team effort that, required a lot of people's very active effort on. So maybe in these last few minutes, I can talk about some of the interesting qualitative behaviors that we've observed from actually running this model and kind of, using it in practice. So one of the things that people do in the climate modeling or in the weather forecasting climate modeling community is look at historical extreme events, right? So you can look at any extreme weather event that has happened in the past that we have data for, start your model at some time right before that and see how well it does at capturing that event, right? So in particular, we decided to look at Hurricane Laura, which struck the Gulf of Mexico on the U.S. coast in August of 2020, and we did a whole ensemble of multiple rollouts at different starting conditions. So you can see this leftmost figure is the ensemble of generated configurations starting from 7 days prior to landfall. And you can see that obviously there's a bit more spread, but so this red line actually captures the mean trajectory of our generated predictions. And it's obviously not perfect, but I don't know. To me, that's just crazy, honestly, to think that these models are able to capture this behavior 7 days in advance with pretty good accuracy was very surprising to see, for me at least. And you can see as we decrease the kind of initial lead time, so as we start a little bit sooner, starting at 5 days before landfall, our predictions are even better yet. And then going down to 3 days, you can see that we actually do really pretty well at predicting the significant curve that it took once it hit land. We were able to capture that pretty accurately. And so that was, even for the climate, scientists on our team, they were pretty surprised by that as well. So that, is a really good result to the extent that I'm aware. And so that was obviously one, one early result that suggested to us that this model is actually, doing something in there, right? Like it's actually able to capture some of these non-expected behaviors, I would say. And so then one of the next things we did after that was to try to see, okay, so that's very interesting behavior in the first place. But now another thing we're interested in is to see how long in advance can we roll out our predictions before they start to, fail, right? You obviously can't predict the weather infinitely into the future. At some point, any prediction mechanism you have is obviously going to fail. And so it's really interesting. People are really interested in testing how long that is, right? how long into the future you're able to accurately predict, essentially, which is a major challenge for all of these kind of weather forecasting foundation models. None of them are able to predict too far in advance. So typically what they look at are like subs. I think it's one too many S's, right? What they typically look at is what's called sub-seasonal to seasonal forecasts, which is more commonly abbreviated as S2S, for obvious reasons. And so these are forecasts that, yeah, extend from sub-seasonal, so yeah, within an individual season to across, maybe from spring through autumn, maybe, but within the time span of an individual year. But these are kind of the longer range predictions that most models have historically done very poorly at. And so, yeah, as it says here, we did 3,000 rollouts with 60 initial conditions, or we did 60 initial conditions with 50 member ensembles out to 90 days, which gave us 3,000 forecasts. And we actually found from these rollouts that AERIS was able to accurately capture realistic atmospheric states and is able to accurately reproduce power spectra even at the smallest scales, which, yeah, Troy. So Troy, I remember, yeah, when we were discussing this and when we were in that meeting, Troy, who's one of the authors on the paper and who has done this, did this for his PhD, and that was just like could not believe it. And he was very skeptical that that these results were actually at 90 days. He was like, is this really? Are you sure this is at 90 days out? And they were. And so he, as somebody who has been working on this for a long time, to see his reaction and be so surprised by that was. Told me all I needed to know about the results. And so I think that there is a lot of interesting, there's a lot of interesting things that remain to be explored. And especially with this model that seems to be doing so well at all of the tasks that we have thrown at it, we're really kind of interested in really pushing it further and seeing what, kind of the limits are. So here again is another interesting, kind of real world case study. So we looked at this one is this is, okay, yeah, so this is the temperature distribution of El Nino. In the paper, we look at a heat wave in London. And so I was a bit confused for a second. I thought I included the other figure. But this is another interesting use case where you can see that, yeah, I don't know. The generated configurations seem to relatively accurately capture like the temporal dynamics of this, rising and falling of the temperature in El Nino, which I think is also something that models have historically failed at or struggled with. And so all of these kind of like what are typically things that trip a lot of other models up on, we have been seeming to do pretty well at. Which is, obviously bodes well for the model. And yeah, so that's really about all I had. Yeah, like I said, neither Troy nor Vaino are here, or Troy nor Vaino nor Jason are able to be here in person to talk more about it. And so you guys got stuck hearing about it from a non-domain expert. So, but hopefully, I think I hopefully captured everything was interesting. And like I said, I'm also more than me and the rest of the team are all absolutely happy to talk more about this with anybody who would be interested in. I personally did most of the like large scale distributed pre-training and was working on this mostly specifically. And so anybody who wants to talk about that specifically, I can go into whatever sort of detail you want. Anybody who wants to press me on climate questions, I'm gonna have to redirect you, but I'm happy to chat in general. Yeah, questions, absolutely.
Hello. I thought Aurora has maximum 1 exaflop. How can it have a 10 exaflop performance?
I believe it is A and B in FP64. Typically way back when and a couple, maybe the older people here at ALCF maybe can correct me. But it was called like the plan was for these like, machines to be called these next level of computing machines. They wanted to reach an exascale of FP64 performance. And so that is now Aurora, El Capitan, and Frontier. And so those are like the exascale systems. And I think in all of the design, I think the goal was to get just over 1 exaflop of FP64 performance. And so this is all so this is actually all using BF16 and train for reduced precision, mixed precision training in PyTorch. I don't remember what we got on the HPC 500 for FP64 over an exaflop. I don't remember exactly what it was. So it is we actually managed to do a bit better than the 1 exaflop that Intel guaranteed us. I don't remember exactly how much better, but apples to oranges. FP64 is just much more arithmetically intensive, and so harder to get as much throughput.
And there are 6 GPUs per node and 10,000 nodes, so around 60,000 GPUs.
So there are 6 tiles per node, and each tile has 2 XPU devices. What? I have that backwards. 12 tiles, 12 tiles per node, which, however you want to call them, at the end of the day, there are 12 assignable XPU devices per node on Aurora, which are equivalent to 12, CUDA 0 to 12 on similar systems. So there's, however, I always get them backwards, honestly, in my head, but there are 12 XPU devices per node on Aurora, each with 64 gigabytes of memory.
Okay, and for the cyclone predictions, like how much time did it take to predict?
To do these generations, that is something I very conveniently glossed over. So one of the main challenges currently is that in order to run inference and run the generation on this model, it's very complicated at the moment due to the fact that we have all this custom window parallelism, the fact that in order to reliably do a forward pass, I need to almost do a global coordination across all of my GPUs in order to just do a single forward pass. And so it's complicated and slow at the moment. I guess there's after that. How do I not have it? I had an extra slide, I thought, down here at the end somewhere. Maybe not. About what is next. And so I guess I can actually just go to the repo. So we are working on trying to distill this model into manageable, runnable kind of individual components that will be much more performant. And so, it's kind of a whole wait, and if you ask me in a few weeks, I will have a much better answer for you than that, unfortunately. But
so it happens in a few hours, you said it's prediction 7 days in advance or 5 or 3 days in advance. So I think it would be, it would give the results in a few hours.
Sure. You can reliably get a few ensembles, I would say, within a few hours, depending on how cooperative Aurora is being. Roughly, I would say I didn't run any of the inference generation specifically myself, and so don't quote me on that, but I believe so. Yeah.
And it's all AI prediction. There's no computational fluid dynamics.
No, just entirely model driven, no simulation based components. No.
Thank you.
No problem.
Yeah, so when you show the 40 billion model, it looks like scaling is pretty good. So probably your network intensity is pretty low in this training model, right?
I missed that last part.
So 40 billion model, if I look at the line, it's almost linear.
Mhm.
I guess you don't lose any efficiency across the up to
Mhm.
120 GPU case, right? So it looks like your network intensity could be pretty low in this training model, I guess.
So we also have, so in the paper, which I didn't include in the slides, but we have a result on the weak. So we also looked at the weak scaling across this like window parallelism and the gradient accumulation stuff to mention. And so yes, there is likely room for improvement on saturating the amount of work that the devices are doing, essentially, is what you're saying, right? Like there's probably room for we could probably improve throughput by increasing the arithmetic intensity at a cost of not at slightly nonlinear scaling. Right?
So 40 billion model is actually you are doing the strong scaling, right?
Yes,
You're
yes,
solving the same problem.
yeah, exactly.
So do you know how much memory usage happen?
How much memory it use?
Yeah, for GPU. I mean, I'm just curious.
That is a good question. Yeah.
Yeah.
So the 40 billion parameters. So yeah, so I think what Vernie was saying is that it's also going to be very heavily dependent on the degree of the various degrees of the parallelisms that are in use, as well as like, yeah, there are other kind of tricks you can try to use to like, saturate, get really like, obviously gradient accumulation is kind of a cheat, right? Like it's essentially just.
I mean, so it depends on the model size that you're trying to train. So I'm assuming if it's somewhere between like 1 billion model, for example, I would say the worst. So again, like Sam said, there could be different ways you can optimize and also like the kind of model parallelism you're including will differ the amount of memory usage. But I would say in a worst case scenario, you can take approximately 4 to 6 times when you're training. And in inference, it is kind of twice, meaning if you have a 1 billion kind of model, I would say at least there will be like 6 to 8 giga for training and maybe like
Maybe 6 to 8 gigabytes.
yeah.
And so it also is going to be very like another one of the main challenges in all of this is that even for a single, in order to even to read in a single quarter degree image, that's like, I don't know, something huge. It's like it's like a 720 by 1440 image with I think like 50 channels. So it's 720 by 1440 times 50. Even in FP16, that's a huge percentage of my available memory right off the bat. And so can only scale my model up to whatever is left after I've already accounted for the data, right? And so that's another one of the big challenges in this is how to even scale up model size when so much of your available memory is just going directly towards having to be able to hold and load the data at the same time.
And your batch size also matters, right? So your batch size and the input resolution itself will take away a lot of your memory. So you're kind of left with whatever, especially in a vision kind of model scenario where your input is an FP16 or FP32, whatever you're going to take. Whereas if you consider the same in a language model, your inputs are like integers. So that way your input size in terms of memory is much, much lesser. So you can have a larger model for a language based versus a vision based model.
Okay. Yes. Okay. Maybe I just want to simply understand. So 40 billion model, let's say if you use 5,000 nodes, right? Then we may have some kind of GPU usage. For example, let's say we use 50 gigabytes, right? And then if we just double up the numbers, node numbers, do we expect the GPU usage be drop to 25 gigabyte or still 50 gigabyte?
Are we doing any zero in this? No.
So there is, in addition to the parallelism, there is also,
But there was only 0, 1.
but it's like a it's like a so it's not actually using deep speed. It's essentially just a you know, hand rolled implementation of optimizer state offloading that we're doing essentially. And so it's it's like a 0-1 based approach for freeing up, another trick to try and free up a bit more memory during training. So it's not actually using, it's very similar to deep speed 0-1.
I mean, worst case, if you're not going to have all these optimizations, right? You will have the same memory kind of replicated throughout the GPU. So every GPU has a replica of the model, at least the model weights, and it has its own like input as a whole or part of the input, depending on what you're doing. But at the end of the day, every GPU is like, it has some weights, it has some input. And of course, the optimizer states is pretty huge, especially if you're kind of using second order optimizers and so on and so forth. So in training, optimizers has the most memory. So it kind of takes up like 6 to 8 times the amount of, so it essentially means like if you have 1 billion weights, like 1 billion FP16 parameters, then the optimizer is going to take like 6 to 8 kind of billions of parameters for just the optimizer. So what we typically do is you don't want to have this replicated on each of the GPUs. So you kind of have a part of it on each of the GPUs. But again, all you're doing is you're moving the problem from being a
memory problem to a compute. It's
probably now compute bound, because if it's too much, then now you're taking time to kind of like
redo all those,
the entire weights across different GPUs.
Yeah, and so it's very much a trade-off.
But having said that, these are all very heavy, compute heavy. So the communication is very less when compared to the compute. So you might kind of get away by doing that.
And honestly, I would say it's I was very happy with the performance results that we saw. Honestly, even if so last year at Supercomputing 24, we had another submission that was a finalist for the Gordon Bell Prize last year. That was using this MPROT DPO, this protein design model. That was a finalist last year, just in November of last year, that had just over 4 exaflops, which was, honestly, is still a remarkable achievement. Honestly, to achieve over 4 exaflops distributed training on 38,000 XPUs at the end of last year was, it was, again, that was another monumental achievement that, so to see how far we have came in just this year is good. I was happy with it. I was able to go to sleep. Hey now, that's all right.